How about a little science quickie tonight? Topic is side-to-side curvature, ball versus flat. So this came up in just a conversation I was having online, and it's about what exactly do we expect to see in terms of side-to-side curvature if the Earth is round as opposed to if the Earth is flat. So here we go. I just made a quick simulation. You're looking at it right here. Here I have, take a look at the scene. It's just the Earth is being represented as a sphere. So we have a sphere and there's a viewer. I've placed the viewer on top of the sphere. Okay, take a look over here. These are the numbers so you can check the scale. The radius of the Earth in this simulation is 20 units, right? So we'll say that's going to set the scale. The viewer then is 0.1 units up, which is the equivalent of 20 miles. So in order to see some curvature, I'm exaggerating things quite a bit. This is a viewer 20 miles above the surface of the Earth, looking at the curvature. And this on the right, this is the view that the viewer sees. Let me show you how that works. The viewer then can look up and down. I'm gonna look up at the sky. I'll look down towards the ground, and that's the view that I see. Now, I do want to stress this is just a quick mock-up to help us visualize. This isn't trying to prove anything. This is just to help us visualize what it's supposed to look like. So this is a fairly low resolution sphere, and what you see right here is the vertex of two polygonal surfaces. So it's not a perfect sphere, it's just a low-res sphere. This is enough to show us curvature, side to side. We can definitely see at 20 miles up a little bit of curvature there. Okay, that's what we're expecting to see. Now, what I want to talk about is why do we see that? When you're way far back, like on the left, when you pull way back and you look at it, you see a very round shape. And that's usually what people are thinking of when they say, I want to see that. I want to see that side-to-side curve. I've got a ring. I'm drawing a ring around the disk. Can we see what that is? That is a ring slicing through the disk. It's just, it's a disk slicing through the sphere. And the sphere pokes up over the disk, right? This is just the disk. What is that? That disk is your horizon. From this location, this is the area that you can see. And to make that more clear, I'd like to just spin the camera around. This is the camera's view. And over here on this view, I'm going to just spin the camera around and look and see. What I want you to notice is that the horizon doesn't go up and down. I mean, it does just because it's low res, but it doesn't rise and fall as I go in a circle. It's a circle, right? The horizon is a circle, and a circle is flat, right? Let's say it again. The horizon is a circle from whatever altitude you're at, and the circle is flat. So what causes side-to-side curvature is not the fact that it's a sphere at all. You're looking at a circle. A circular cross-section of the sphere is all you're looking at. In fact, let's get rid of the sphere and just look at the disk. Let's just look at the disk here, and we'll pan around and we'll see it's the same, right? It's the same horizon. I've boosted it out just a little bit so that you can see it against the blue. But it's the same horizon, same curved horizon is what happens regardless of whether you're looking at a sphere or a disk. It's the same, right? So the question was, is it just perspective that causes this, or is there some other kind of curvature? No, it's just the perspective, right? It's just perspective. Let's crank it up. Let's head up to 200 miles up. So from 200 miles up now, I've moved the viewer up. You can see the viewer is substantially higher up off the surface of the Earth now. We should see more curvature. And why is that? Is that because we see more of the sphere? Yes, sure, that's one way of describing this. But my preferred way of describing it is because the horizon is lower. And we'll see that in a sec. Let's bring in the horizon. I've got a horizon again, did the same deal. And now the horizon is larger because I'm farther away, I can see more of the sphere. But the same exact thing happens where as I rotate around, the horizon is what I see, no matter what angle I'm looking at. Now this, at first, this really bent my mind when I thought about this. That means I'm looking at a flat disk. I'm not looking at a curved dome of the ball, right? All of this dome, let's take a look here. All of this dome here, this dome on top of the disk of the horizon, what is that? That is all of this space in the foreground. The dome does not poke up above the horizon. The dome is in the foreground. That's the near field, is what we're seeing, is this dome. The disk, which is completely flat, is the gray lines. If I take out the dome part, right, let's just take that out completely and just leave the disk, the horizon stays at the same place, no matter which angle you look at, right? And that's weird. I'm looking at a flat disk right here in the simulation, but it's curved. Why is that? All right, I don't want to go all the way out to the garage to get a hula hoop, but I have a spool of cable, a reel of cable here, and that's round. That's round enough. Okay, this is my disk, right? It is flat. We'll say it's flat. Boom, boom. Round this way, but it's flat. This is the flat Earth disk, right? At eye level, boom, put it at eye level. Try this yourself. Grab yourself a hula hoop and do this. At eye level, that creates a flat horizon. Everywhere you look is flat. But if you drop it down below eye level, can you see that on the video? Just drop it down below eye level and take a look. Now, it looks curved to you. It looks curved. But notice, if you turn, any place you look is at the same height, right? It is only as it goes towards the sides of your vision that it drops downward, right? So try that with a hula hoop and you'll understand what I'm trying to explain. And let me show you here with my disc. Okay, there you go. I've got my viewer looking straight ahead. Boom, it's flat, right? That is a flat horizon. But as I move up, we start to see the curve. In fact, let's get right here and let's tilt the camera down a little bit so that as I move, there you go, I'm looking down at the ground. Looking down at the ground, I can still see the horizon across the top, very flat. Now I'm going to rise up and see what happens with a flat disk with my horizon. Here we go. Oh, look at that. It's starting to curve at the bottom of the camera, right? And yes, that is perspective. That is, that's the perspective calculations. That's the effect of perspective. Keep in mind, if I rotate this point, mark this point right here, that's going to stay steady, as are these points on the left and right edges that are definitely sloping down away. Okay, so long story short, that is why you see a curve. It's not the dome of the sphere that you can see. You can never see the dome of the sphere. All you can see is the horizon. And the horizon is a disc shape. It is a circular cross section of the sphere. Now that's pretty interesting, and if you're going to go into the flat Earth versus round Earth. We should look at some flat examples and see what they do. Disk Earth. We are at 20 miles up. Boom. It's flat. From only 20 miles up, the disk Earth looks pretty flat. We have to go up higher to get that. Now, this is surprising. When we were 20 miles up on the sphere Earth, I said the horizon was a disk. So shouldn't it be the same? The disk Earth and the sphere Earth should look the same. No. And the reason is because the horizon is somewhere below the top of the ball, right? In fact, let's go back there. Let's go back to the 20 mile. Let's show the horizon. There's the horizon. The horizon isn't at the top of the ball. The horizon is below the top of the ball. I am currently, the viewer is 20 miles up off of the very tippy top peak of the ball. And then the horizon is, many miles down below that point is where the disk slice takes place. We can do the calculations there if you want, but that's why you get a much more exaggerated curve with a round Earth than you would with a disk Earth. So it isn't the dome of the blue inside that ring that creates the horizon. The boundary between water and space, or whatever that is, right, is the gray disk, which is a cross section of a sphere. Okay? And that means, when we were discussing this earlier, I was discussing this with somebody on GreaterSapien's channel, and I was saying, what do you mean? When I say the curvature, the left to right curvature, I mean this. I mean that the disk of the horizon is below eye level, and therefore I can see it sagging down at the sides due to perspective. And he was saying, yeah, but what about the other thing? And I'm like, well, what other thing? I don't think there is an other thing. And hopefully this shows why. Okay, let me hit the editing room and we'll see where this goes. Okay.